It's a great pleasure to introduce Professor Saïd Hamadene. Professor Hamadene is a leading specialist in probability theory and stochastic analysis. His work has had a major influence in the development of modern stochastic control theory and its application. He obtained his PhD in mathematics in France and has built an outstanding academic career at University, where he has held several important academic positions as associate professor, and senior researcher. Professor Hamadene is the author and co-author of a very large number of scientific publications in highly respected journals in probability and applied mathematics. His articles are widely cited and have become standard references for researchers working in PDEs and stochastic control. In addition to his research achievements, he has supervised many PhD students and contributed to the formation of several generations of researchers in stochastic analysis and control theory. I had the privilege of being his first PhD student, which gives me a strong appreciation of not only his scientific qualities, but also the human one. Today, Professor Hamadene will present a lecture on stochastic switching problem with signed switching costs. So the floor is your side.
Thank you, Sam, for the introduction. Thank you very much, Rafiq, also for inviting me to this nice conference. I'm going to speak on stochastic optimal switching with, switching payoffs which are not necessarily, which do not have necessarily the same sign, which could change sign. As you can see, the title is here. And this is joint work with two Moroccan guys from Agadir University, and who are Brahim El-Asri, who was my previous student, and Souheil Mazid, who is the student of Brahim El-Asri. Yeah, so you can see from generation to another one, and it's very nice. I'm going to start. Yeah, so the outlines of the talk are the following ones. I'm going to motivate and to speak also about the setting of the switching problem. So I'm going to introduce the framework of signed switching costs and which of problems the signed switching costs imply. Then I will move to the verification theorem, which I'm going to show that it is satisfied, and I'm going to exhibit the optimal strategy. And finally, we will deal with the Markovian case of randomness and consider the RGB system of PDEs, which is associated with the switching problem. So, if you have questions, just ask for your question. You can ask for you don't need to wait up to have finished the talk if you want to ask for questions. The motivation and the setting of the problem is the following ones. So here, after Beers-Brown motion and if on probability space omega fp, whose completed natural filtration will be denoted by ft. In my opinion, the best way to introduce switching problem is to consider power plant C, okay, which produces electricity, but the electricity cannot be stored. When it is produced, it should be almost immediately consumed, and then the production should be made if there is enough profitability in the market. Otherwise, it doesn't matter to produce. If, for example, say if we speak about the Western countries, if the weather is stringent, in this case, actually, especially in winters, in such a case, actually, it matters to produce electricity because, I mean, people they ask for power, and then in order to heat their houses and so on, and then I mean, in this case, the prices they prone to they are prone to be high, and in such a case, it matters to produce. Now, if the weather is rather mild, especially in winter, in this case, the demand for electricity is rather low, and the prices they are low. In such a case, maybe you should avoid, if you are the manager of the power plant, you should avoid to produce electricity. Yeah, is it okay? Do you have question?
No, no, no question.
Okay. So, yeah, we will suppose that the power plant has M modes where M is greater than 3. Why if one mode, yeah, there is no switching problem. If M is equal to 2, the problem is dual. I mean, the production is dual. Either you produce or you do not produce. Okay, so in this case, actually, the problem is rather much more simple. So it matters to consider the case of M greater than 3 modes. For example, the mode 1 is no production, mode 2 normal mode of production, and mode 3 is intensive one. In this case, actually, for example, you are in mode 1, you want to switch, so you have two choices. Either you go to mode 2 or you go to mode 3. And then, I mean, you should choose according, once more, to optimality of the yield. If you have only two modes, if you say, for example, no production and normal mode of production, if you want to switch from mode 1, you go to 2. And if you want to switch from mode 2, you go to mode 1. You don't have choice. Okay, this is why I mean, the interesting framework is to consider M greater than 3. As I told it previously, electricity cannot be stored when produced. It should be sold and consumed. Then the manager of C will put it dynamically in the most profitable mode. Once more, it doesn't matter to produce. If the price of electricity is low, it matters to produce if the price of electricity is high.
And
So,
the change of modes is randomly or
yeah, I'm going to speak about this
okay,
now.
okay.
Okay. So if C is in mode I, okay, if C is in mode I, the yield and work it works during a short period of time dt. The yield is given by psi I of t omega dt. Psi I could depends on t, depends also on omega. The switching when you decide to move, when you decide to switch from one mode to another one, it induces a payoff which is equal to Lig of T of omega, which is stochastic, which is an adapted continuous stochastic process. Now I'm going to ask for the question which is asked for by Professor Rafiq, which is related to the uh, switching strategies. Management strategy, or I mean switching strategy of the power plant has two components. One of them is delta, the other one is psi. Okay, delta is an increasing sequence of stopping times, which means that at tau n you decide to switch, and when you decide to switch again, it will happen on tau n plus 1, and then necessarily tau n is smaller than tau n plus 1. Roughly speaking, the stopping times tau n, they are the times where the manager decides to switch to switch the power plant from one mode to another one. The second component of management strategy or switching strategy is Xi, which is equal to Xi n, which is equal to this sequence, Xi n, sorry, which is equal to this sequence. Xi n is roughly speaking the mode to which the power plant will be switched from its current mode at time tau n. Okay, so psi n is a random variable which takes its values in G, which is the set of modes, and psi n is f tau n measurable, which means that when the manager decides to make a decision to switch from at tau n to switch from psi n minus 1 to psi n, this decision is made according to information which is available at time tau n. Then psi n is a random variable which belongs to G, this set of modes, and it is f tau n measurable. Yeah, psi n is nothing else but the new working mode chosen at time tau n for the working of the power plant. The pair delta psi is called the switching strategy of management, or switching strategy of management of the power plant. So, do you have questions so far? Okay, let's go. Wait a minute. Oh. Sorry. Now, what about the payoff? Yeah, we are going to introduce stochastic process U, which describes the modes. I mean, the working modes of the power plant. So we suppose that U0 is equal to 1, which means that we suppose that at the initial time, the power plant is in mode 1, and ut is equal to psi n if t belongs to tau n plus. What does mean tau n is nothing else but the mode that the manager has chosen at time tau n to which the power plant will be switched. Okay, so ut describes the working of the working modes of the power plant along with time. So when a strategy delta psi is implemented, the yield is given by this quantity, which means that, I mean, here, what's this? This is the instantaneous. This is the instantaneous utility, the yield which is produced by the power plant, and here we have the switching payoffs. Okay, here this minus this sum, this sum is nothing else but the switching payoffs, and the GUT is the terminal payoff. Okay, GUT is the terminal payoff. So this is the yield which is given by which is the yield of the power plant when it is run under the strategy delta psi. Okay, so the process U is one-to-one correspondence with delta psi. I mean, if you give yourself U, you can recover delta psi. If you have delta psi, actually you can define U in one-to-one correspondence. Now, LIG have said that they do not have necessarily the same the constant sign. When LIG tau is strictly greater than 0, it means that when you switch from I to G, it's a cost, since here you have minus. And when Ligt is strictly negative, here you have minus, that becomes positive, which means that it contribute positively to the payoff. It means that in this case, this Lig is nothing else but, I mean, a subsidy. It's a profit. Okay, we can find, for example, in the economic sphere, especially, we can find examples where when you move from one mode to another one, you don't pay, but you get subsidies, especially state subsidies. If, for example, car makers, for example, they are urged to move from one type of energy for the cars to another one. For example, here now in those days in Europe, the government urges car makers to switch from from oil. I mean, working car makers, working cars to electric working or running cars. So in this case, actually, you get subsidy. It's not a cost when you decide to switch, but it's a subsidy. You get money, and this is the meaning of signed switching payoffs or signed switching costs. Wait a minute. Okay. Up. So the problems we face, they are the following ones. Since the Lig, okay, when the Ligs they are positive, you don't have problem. Why? Because basically here you have minus, and then if you do nothing, this is finite. If you do something, you withdraw a positive quantity. The G delta Xi do not explode. Okay, it does not. There is no explosion phenomenon. Uh, and then when Lig is positive, the problem is well posed at any case, which is not the case when Lig could be negative. If Lig could be negative, you have here minus. It is this sum could become positive, so you should prevent, I mean, the explosion phenomenon. You should prevent to have here, when you take the supremum, it will be equal to plus infinity. Okay, so this is the meaning of the well-posedness of the problem. So once we have put, I mean, the appropriate assumptions in such way that the problem is well posed, do we have an optimal strategy? What can be said about the existence of an optimal strategy? Does a strategy delta star psi star which satisfies this property exists? So what can be said about this sum? Usually, at least formally, we can say that an optimal strategy exists. But I mean, especially for practitioners, I mean, it's bit. I mean, it's rather say not clear if you say that an optimal strategy exists. Usually practitioners, they need to have the value of this quantity. If you don't have the value, is it possible to have some of its properties? It can you I mean, approximate it? Can you simulate it, and so on? All those questions, I mean, get into stake when you deal with this problem. So just a remark here, this quantity is nothing else but this quantity, oh, sorry. Yeah, this quantity is nothing, the remark, the quantity supremum over delta Xi of J delta Xi is nothing else but the price of the power plant in the energy market. Because what's the price of, I mean, a power plant? It is related to the commodity, to electricity that it can produce. But if you run it in an optimal way, okay, it should be not run in a random way. I mean, you should run it in an optimal way, and then you get this quantity capital Xi, and then this is exactly the fair price of the plant in the energy market. So the model also fits for the change of technology for corporate. I mean, it has spoken about car makers. This, I mean, you can find also switching problems in the change of technologies. The management of portfolio allocation of life insurances in a high financial market. When you, for example, you decide to switch from one asset to another one in order to, I mean, to have good yield for your portfolio or for your money. There are also some models which are related to cyber security, which can be tackled by using optimal switching problems. So since I mean we are in Saudi Arabia, the management of crude oil fields is also switching. I mean switching problems, because if oil in the market is low, in this case actually it doesn't matter to produce, because if you produce you will lose money. But if the price of oil in the market is rather high, actually in this case it matters to produce, because I mean you get good revenue. So the crude oil fields, yeah, can be the management of crude oil fields can be tackled by using optimal switching problems. So I should say that the problem is rather old, and there are several papers on this subject, mainly in the case when switching payoffs, they are non-negative, and plus some other appropriate assumptions in such a way that the problem will be tackled and solved. So the framework of signed switching payoffs is the following one. First of all, I mean, we are going to assume that the LIGs, they are increasing or decreasing, okay? For any IG which belongs to this G, calligraphic G, this mapping, the stochastic process is increasing or decreasing. And mainly, or more importantly, the LIG that should satisfy the triangle inequality, which means that LIG is strictly smaller than LIK plus LKG for any K which is not equal to, which does not belong to this set IG. I mean, K should be should not be equal to I, or should not be equal to G, because with this condition, otherwise, I mean, if K is equal to I or is equal to G, I mean, the problem is ill-posed, and there is, I mean, this inequality cannot happen. Then, I mean, the LIGs, they should be monotone. All of them, they should be increasing or decreasing. I mean, you have only one monotonicity, okay? All of them, they are increasing, or all of them, they are decreasing as stochastic processes. And this inequality, the triangle inequality should be satisfied. And actually, we need this consistency condition, which is satisfied by the bequests, the terminal payoffs GI. They should be square integrable, and the GIG should be greater than the maximum. Here, this is G, sorry, not I, okay? This is G, which belongs to calligraphic G minus I. I mean, G should be different from I, GG minus LIGT. Yeah, the bequests should satisfy this inequality. Yeah, those are the assumptions. Now, the triangle inequality implies the non-free loop property, which means that if instantaneously you go from one state to the same state and you make loop, then you should pay something. It's not for free. Okay. So if you have modes I1 up to AK with K greater than 3, okay, with k greater than 3, and I1 is equal to AK, then Li1, I2, T, and so on, plus Ik, I1, T. This is strictly greater than 0, which means that if you make instantaneously loop from I1 up to, and you come back to I1, and you pass through I2, I3, Lik minus 1 AK, you should pay something. It's not for free. Okay. And the non-trivial property actually implies the triangle inequality implies the non-trivial property. Why? Because here this quantity is nothing else. Here you apply the triangle inequality, which means that this sum here, which means that the sum here, okay, is greater than that one, okay, strictly greater than that one, and you do the same with the sum, up, and at the end of the day, you will get I1T, which is equal to 0, as we have supposed it. Now, are there cases where actually we have monotonicity and we have non-free loop of the triangle inequality satisfied? Yes. Yes, if we take L, we have M is equal to 2, and L1, 2 is equal to minus 1, L2, 1 is equal to 2. I mean, those conditions, they are satisfied. At the end of the talk, I will give also much more elaborated examples where those conditions, they are actually satisfied. Yeah, so here we are in framework of finite switching payoffs, because when we move from 1 to 2, we get a subsidy of 1, and if we move from 2 to 1, yeah, it's a payoff which is equal to 2. So, I mean, since there are signed switching payoffs, the notion of admissibility is modified. Okay, it should be updated. So switching strategy delta psi is called admissible if once more stopping times it is an increasing sequence of stopping times, and this condition is satisfied, which means that, I mean, omega by omega, we are allowed to make only a finite number of switches. Okay, omega by omega, we are not for specific omega, we are not allowed to make an infinite, an infinite number of switches, which means that, for example, for omega 1, we make 20 switches. For omega 2, we make, 30 switches, and so on. Okay, but things should be finite. Okay, with omega by omega, we make a finite number of switches. Psi n is a random variable, such that once more, here we change mode. Okay, here it means that we change mode. The probability that psi n is equal to psi n plus 1, tau n is strictly smaller than t. This is equal to, when we switch, it is equal to 0. And in order that the strategy delta psi should be admissible, we add conditions which are related to the n partial payoffs. The n partial payoff is defined like this. This is the payoff when we make only n switches. Okay, when we make only n switches inside this framework, inside the framework here. Okay, inside the framework here. Okay, yeah, here when we make only n switches, and those n partial payoffs, they should satisfy this quantity, this quantity. So note that since we have omega by omega, we make only a finite number of switches, it means that if you make the sum here, this sum, which seemingly which seemingly is infinite. I mean, you have an infinite number of terms, but really you have only a finite number of terms because those tau n strictly smaller than t. Since the delta psi, I mean, we require that it should satisfy this condition. It means that in this sum, yeah, in the sum you have only a finite number of terms. Okay, this the number of terms will move with omega, sorry, or could move with omega, but still that it's only a finite number of terms. This is the definition of admissibility. Let's go ahead. Now we have a proposition which is mainly related to those the n partial payoffs. They should not explode in order that the problem will be well posed. They should not explode. And actually, they do not explode since we have assumed that the LIGs they are increasing and they satisfy the triangle. Since we have supposed that the LIGs they are monotonic, not increasing, but monotonic, and they satisfy triangle inequality. So if the switching costs they are increasing here, in a way, this is the n partial, capital N partial payoffs. Okay, it is here. They are smaller than this random variable, which is square integrable. Now, if they are decreasing, we have the same. I mean, we have this estimate here. It's when they are increasing, the the random variable is in tau 1. When they are decreasing, the random variable is in capital T. Okay, yeah, this is the main point in order to make that the problem is well posed. So how we are going to show, for example, the inequality 1? Yeah, we'll do the proof is done by induction. Okay, by induction. So the inequality 1, if n is equal to capital if capital N is equal to 1, the inequality is actually true. Okay, and then we suppose that it holds up to capital N minus 1, and we introduce those sets of D, which is the set of omega, such that L psi n minus 1 psi n tau n is strictly negative, and then we will show that once more those quantities they are dominated by this quantity here. So minus C delta psi capital N will split it into two terms. The one omega is in D, it is here, and one omega is in the complement of D, which is here. Now let's focus on this the first term. The first term is actually dominated by that one. Okay, dominated by that one. Why? Because basically, since we are in the complement of D, we are in the complement of D, which means that this quantity is positive. Okay, and when you take the minus, when you have looked to this minus, the sign becomes the sign becomes negative, and it is smaller than this quantity. And on that we'll use the induction hypothesis, which means that this term is smaller than that one. Okay, for this term, it is smaller than what we want to prove. Okay, what we want to prove. Now we will focus on this second one, and here gets involved the monotonicity of the Lij's on the one hand and the triangle inequality on the other hand. So since delta psi is, delta psi verifies those this property and that one. Okay, we have tau n is strictly smaller than t is included in tau n minus 1 strictly smaller than t, which means that the indicator, when you take the indicator here, it is smaller or equal to the indicator here. And since the Lij's, they are increasing, which means the value of this value is smaller than that one because tau n comes after tau n minus 1. Now, when we have to look to minus the sum when omega belongs to d, we will split it into the terms up to n minus t minus 2 minus the term which corresponds to tau n minus 1 and the term which corresponds to tau n. But since we are in d, this quantity is negative, minus becomes positive. The indicator of tau n strictly smaller than d will be majorized by the indicator of tau n minus 1 smaller than t, which means that here we have the inequality. If we replace this indicator by that one, once more we have this inequality, which is related to the increasingness of the Lij's. Then if you take the opposite, you have this term will be smaller than that one. Okay, which means that this sum is written up to n minus 2, and it is written on terms where tau n is cancelled and it is replaced by tau n minus 1. And we are going to see what to do now. Yeah, so here we are going to use the triangle inequality. Okay, don't forget that xi n minus 1 is not equal to xi n. Okay, which means that we can use the triangle inequality, and then this is greater than L xi n minus 2 xi n. Okay, by using the triangle inequality. When you take the opposite here, what you get this one. You get this quantity. Here we have only n minus 1 terms. So now we arrange things in such way that we are going to use the induction hypothesis and once more to infer that the inequality holds true. Okay, so what to do? We have here it's the same. Okay, we disintegrate L xi n in such way to have random variables. Okay, to have random variables which are f tau n minus 1 measurable. Okay, which are f tau n minus 1 measurable, and the constant is actually f tau n minus 1 measurable. Here we had this expression is nothing else but this integration of xi n. We may take the sum over L which belongs to G, and here as you can see you have the indicator xi n equal to L, but here xi n is replaced with L. Okay, and then on that we will use the induction assumption by introducing new strategy which falls inside the framework of admissible strategies. Okay, admissible strategies. I mean the two first points. Okay, the two first points. Okay, and then sorry. Yeah, sorry. Yeah, and then here. Yeah, sorry. Yeah, it is here. Sorry. yeah, and we introduce, I mean, we had some trick in such way to introduce, I mean, a new strategy in order to write things in an appropriate way. And then we use on this we use the induction assumption, and it is smaller and it is smaller than this maximum. Say when you make the sum over L, which belongs to G, 1 psi n is equal to nu. This is equal to 1, and yeah, we have this inequality, which means that there is no explosion of this capital N partial payoffs. The same here happens. Okay, the same here happens. Just I mean, work in capital T. Okay, now let's come back to the verification to the verification theorem and its solution. I mean, we can find we assume, I mean, the assumptions that we have introduced at the very beginning, especially the triangle inequality on the LIGs. There exists continuous stochastic process YIZIKI, which satisfy system of reflected backward stochastic differential equations. Thus, what's the specificity of the system is that here it is backward equation, because yi at capital T is equal to gi. Okay, yi at capital T is equal to gi. As you can see here, you have, I mean, this is reflected BSD. Yeah, this is the obstacle, but the main thing which needs to be said is that the obstacle depend on solution. Okay, you look for y1, yiziki for I is equal to 1, 2, 3. If you take m is equal to 3, but here, as you can see here, the obstacle the obstacle depends on the on the solution. And actually the KIs, they are in stochastic increasing processes. I mean, in this equation, KI is in a way it's weight. It's weight in such a way that this inequality will be satisfied, but still that you are not going to add an arbitrary weight. You should add only what is necessary, which means that, I mean, we should require this Skorohod condition satisfied, which means that, I mean, yi ki, which means that ki increases only when yi touches the obstacle. Okay, this is a system of reflected BSDs with interconnected obstacles. I mean, the obstacles depend on the solution. There is a solution for this system. So maybe a word about the existence. The solution of the system is constructed in in a recursive way. We take for I is equal to 1, 2, 3, for n is equal to 0. This is this quantity. Now, for n greater than 1, we have a sequence of reflected BSDs, standard BSDs, because here the obstacles, okay, they are already determined at step n minus 1, so which means that those equations, they are only reflected BSDs, and this sequence is well posed. Okay, there's no problem of definition of the of this sequence. So we know that there is link between the solution of a reflected BSD and Snell envelope of stochastic processes. If you add to yin, if you add this quantity, you get Snell envelope. Okay, you get a Snell envelope of stochastic process, of the stochastic this stochastic process. Okay, so what's an envelope of a process? If, for example, you give yourself U, okay, you give yourself U, which could be, for example, a payoff. What's the snare envelope of U is nothing else but this the red, the curve in red. This should be understood as the smallest smallest decreasing function, which majorizes the given one, which is U. As you can see here, tau star is the optimal stopping time. If when you stop at tau, you get U tau. When it is optimal to stop, it is optimal to stop at tau star. Yeah, here snare envelope is continuous, and then you have an optimal stopping time. There are also other examples where there is no optimal stopping time, but we can define the snare envelope of U. Okay, here as you can see, U has a negative jump. The negative jumps of U could imply jumps for the snare envelope. And when with snare envelope has a jump, since it is more or less a super martingale, its jumps, they are negative. And when there is jump of snare envelope, here you have the left limit. You have left limits. They are equal because it is the smallest, decreasing function, which majorizes U, and the jump of the snare envelope is smaller than the one of U. This is what can be said about the snare envelope of stochastic processes. Now, if we introduce for N, we introduce those sets of strategies, which are, sets of strategies where we are allowed to make only at most N switches, since tau N plus 1 is equal to T. In one strategy belongs to DIN. We are allowed to make only at most N switches. Then there is a characterization of YIN through this payoff. Okay, this payoff. This is the optimal payoff when you use strategies of DIN. So since tau N plus 1 is equal to T, the sum here stops actually at N, but minus this sum is nothing else but the small n partial payoffs. Okay, so this characterization, the characterization here implies that Yn is smaller than Yin plus 1. Why? Because we have more freedom when n increases. So you have this inequality, and there is no explosion of Yin because, as I told it before, this quantity, okay, this quantity is is dominated by the quantities that have been highlighted in the proposition that we have already shown, which is satisfied since we have monotonicity and we have also the triangle inequality. Okay, we have here this inequality. There's no explosion of those Yin. Okay, no explosion. So we can take the limit. We can take the limit up to a term which does not depend on n. Yin is snare envelope. It is a super martingale. Okay, super martingale. When you have an increasing sequence of super martingales, here the Yin, they are continuous, then the limit is Cadillac. The limit is Cadillac. This is this is standard result. An increasing sequence of Cadillac super martingales converges to Cadillac super martingale. Here the Yins, they are Cadillac. Then Yi is Cadillac. So as I told it previously, if you want to have optimal stopping times, and we need optimal stopping times. Why? Because basically switching problem, yeah, they are successive stopping times that you should exhibit. In order that they exist, you need continuity. Okay, you need continuity. The Snell of yi verifies also this property. You take here the limit, you take here the limit, and throw by using the by using the continuity of the Snell envelope operators through increasing Cadillac stochastic processes. You can take the limit here. You can replace yin by yi, and you do the same here for yk n minus 1. Okay, so yi verifies this quantity. It can be expressed through Snell envelope up to a term at least. Okay, now yi is continuous. Why? Because yi, as I told it previously, it's more or less super martingale. If it has a jump, it is negative. When the Snell envelope has a negative jump, the stochastic process U, has also a negative jump, and you have also the equality between the left limits, which means that if at some time t0, which could be a predictable stopping time, you have a jump of yi, okay, then there exists g such that yg will jump also, because the ligs, they are continuous, and you have the equality between the left limits. Okay, but since yg will jump at t0, you do the same as we did for yi, and at the end of the day, you replace here at the end of the day. Since, I mean, the set calligraphic G is finite, you can find the loop G1 up to Gp minus 1 such that this equality is satisfied. But this is not G, but this is capital, this is L, this is L, this is L, this is L. Yeah, which means that the non-free loop property is violated, which means that, I mean, yi cannot have a jump, and then yi is continuous. Now, since the yin, the increase to yin, they are continuous, yi is continuous, just use Dini theorem to show that the convergence holds in L2. If you come back to the equation satisfied by yin, we can show that zin also they converge to zi dt times dp square, and the kan, they will converge uniformly to ka. At the end of the day, we get that the yizi, okay, we define zi like this, ka like this, then yizi ka, they verify the verification theorem. Okay, then we have existence. Now, how to exhibit the optimal. There exists an optimal strategy. Tau1 star will be the same if psi if at the very beginning the system the power plant is in mode I. What will be tau1 star the first time that yi we reach the obstacle? Okay, we reach the obstacle. What would be psi1 star? It is the optimal index here. Okay, it is the optimal. Then you skip to y psi1 star. What will be tau2 star? It will be the time when y xi1 star, xi1 star, sorry, will reach the obstacle, and xi2 star, it's the optimal index, and so on. Okay, in that way, we construct the optimal strategy. We have admissibility of this strategy because of the non-free loop property, which is implied by the triangle inequality once more. And we have also, in following the strategy U star, we can show that this is satisfied. What's this? Okay, what's this? This is only this is nothing else but the n partial payoff, and we can show that this inequality, I mean, those n partial payoffs which are related to U star, they are finite, and finally y1 yi0 is g of U star. The way in which U star is constructed implies that yi0 is greater than gu for any u such that xi0 is equal to I, which means that U star is the optimal strategy. So we have 2 minutes. I will finish. So we have shown that an optimal strategy. The problem is well posed. On the other hand, an optimal strategy exists. Now, what can be said about the Markov framework? Suppose that the randomness stems from xtx, which is a solution of stochastic differential equation of this type. We put appropriate assumptions on B and sigma in such a way that the solution will exist and is unique. We suppose that psi I is a deterministic function of this stochastic process. The gi's, once more, they are deterministic function of xt, and the ligs, okay, they do not depend on x. Why? Because basically we have supposed that the ligs, they should be monotonic. So if they depend on L, it becomes rather difficult to make them monotonic. This is why we have supposed that the ligs, they do not depend on x, they depend only on time. So in this case, we have the solution of the system, and there exists deterministic continuous, there exists deterministic continuous functions vi, which express those vi's, and these vi's, they are continuous of polynomial growth and viscosity solution of this system, which is Hamilton-Jacobi-Bellman system, which is associated to the switching problem. Once more, what can be said about this system? As you can see, Vi should be greater than this maximum, and this which is the obstacle, and the obstacle depends on the solution Vg. Yeah, the comparison of sub and super solutions of polynomial growth holds for this system, and those Vi's, they are the unique viscosity solution in the class of functions which are continuous and of polynomial growth. So there is another example. I have given one in the case when m is equal to 2. If you take m is equal to 3, t is equal to 1, sigma is equal to 1.5, b1, m is equal to capital I or capital G equal to, this is the set of modes. Psi 1 doesn't matter. You can take functions like those ones. So this is positive. L12 is positive. L13 is positive. But L21 changes sign, because if t is equal to 0, this is equal to minus 0.4, which is negative. And when t is equal to 1, t is equal to 0.6, yeah, it changes the sign. This quantity, this L changes the sign, and that one changes the sign. We take the GI. As you can see here, we have a framework where we have signed switching payoffs. They are not necessarily positive, and the problem, there is an optimal strategy. V1, V2, and V3, they are here. Okay, they have been implemented. Those are some numerics. Now there are some extensions. We can have, for example, monotonicity on 0T1 and another monotonicity on T1T. What to do in this case? To solve in T1T and then to solve on 0T1, but the terminal value here will be the solution which is obtained in T1T. I mean, here we have only 1 point T1, but we can have k points T1, which are the sequence T1 up to Tk, they are increasing. What to do in this case? To solve in Tk capital T, then in Tk minus 1 Tk, and so on up to the solution, the resolution in 0 up to T1. But what to do when you are prone to solve on Tk k minus 1 Tk, the terminal condition should be the solution of the problem in TKT, which is considered in TK, okay? Because you are, in order to pass, to make some concatenation. Yeah, here T1 up to Tk, they are fixed, but they could be stopping times. I mean, things work exactly in the same way. Some references about the stroke, okay? Some references about the stoke, and the list is far from exhaustive. So thanks for your attention. I have taken a bit more time. Sorry. Yeah. So this is what I've been able to do, and I hope you have enjoyed my talk. Thank you.
Thank you, Said, for this nice talk. Some questions, please. I have a general question. Could the framework be extended to mean-find interactions or multi-agent switching games?
I mean, the the mean field, we can do it. The mean field, what can be done, I mean, some kind of Makin-Vlasov framework. Yeah, here in this system, we can add some, instead of taking psi I, we can, for example, take psi I of u and the expectation of yi u. There is no problem for that. We can even take the law of ui. Yeah, this is what can be done. I mean, we can consider the Makin-Vlasov framework. It does not raise major problems with respect to especially paper which I did with Balam Jihish and Romuald Deli, where psi I, instead of having like this psi I of yi, but we can have psi I of yit and the expectation of yit. Okay, Makin-Vlasov framework. This is on one hand, it does not, with respect to that, it does not raise major problem. Now, for the switching game, it's the problem. Is much more complicated, because you are a bit lost, since here, I mean, the player, I mean, the controller keeps track, moves from one mode to another one, and he knows the mode to which the unit has been moved. But if you have a game, you have modes for one player and modes for the other player. Each one can switch. So the one of them will be lost. Okay, will be lost because you don't know what the other when the other does, and then this situation creates some. It's more or less cumbersome.
Okay, thank you. You prove the existence of the optimal strategy of an optimal strategy.
Yeah,
I mean, there are unicity of an optimal strategy, or we can.
We don't know, but certainly there could be. We can find cases where there are several
Okay. In this
I
case,
mean,
in this case,
we can range, yeah, in this case, I mean, we were interested to find an optimal strategy because mainly what is important is the y-i's, okay? The y-i's. The y-i's, they are the supremum. So are they are they reached by U star or by U1 star? Yeah, it could be interesting when we have looked to some cases, but at the end of the day, they give exactly the same value. And this is the most important thing. Okay, but maybe if we choose appropriately the GIs, the PCIs, and the LIGs, we can find several optimal strategies for the problem. Yeah,
okay.
but we did not focus on that.
Okay. Other questions, please?
Yes, please.
Yes, Helmi.
Okay, thank you very much, Professor Said, for the nice presentation. So actually, I have two small questions. So the first question is about the assumptions. So is it possible to obtain the well-posed switching problem without the triangle inequality? So for example, by imposing different conditions on penalty, like on the number of switches or something like this?
I should say that I'm working on that.
Okay, it's good.
I'm working
Yeah.
on that, and I have made some progress.
Okay, that's good. So, otherwise, actually, so you said in this remark that
And
the
so I'm so and then I should say that I'm not the only author of that, so it's a bit complicated for me to say
I
something.
got you. Yeah, I
Sorry,
got you.
but I should tell you that I am working on that. I think that the paper will be ready soon.
Okay, so I would like actually to say it very soon. So, otherwise, in this remark, you said that the triangle inequality implies non-free loop property.
Yeah.
So, could we just remove this triangle inequality and keep just the non-free loop property? Because you already use it in the continuity for the yi. This is
Yeah,
actually was the limit process.
yes.
You are using just the
Yeah,
I mean the
can
sure.
we keep only this is your question. Can we keep on
Yes. Yeah.
non-free property?
Uh,
I don't know. Yeah, this is an open question.
Yeah, because that one is implies that one. So I'm
Yeah,
gonna just
yeah,
keep it with
yeah. This is
non-free
an
loop
open.
property. That's
Yeah, this
yeah.
is this is an open question.
Okay. So otherwise, I have more questions about the reflected backward stochastic
Yes,
differential
please help me.
equations.
I hope you are
So
fine. There you are.
oh, I'm good. I'm good. Thank you so
Okay.
much. So actually, so you are using the finite switching causes. So which is your actually, it could be like subsides or it could be like causes. That's right. And in the standard reflected backward stochastic differential equations, we are using the k like a push in the
Yeah,
minimal way.
yeah,
Okay, but here, if you can see in the question number, in the equation number 5, if you can see in this slide, so if the switching cost is negative, in that k, what is the in that case, what is the k mechanically represent? Probably we can have problem with the comparison theorem as well.
yeah. Ki is related in order to keep this condition in order to keep this condition
Yeah,
satisfied.
yeah.
Okay.
To keep the y above the
Yeah.
obstacle. That's
It,
right.
it,
But if
it doesn't.
the L is negative,
Yeah. It
what
doesn't
can we
matter.
do?
It doesn't matter whether or not Lig is positive.
Okay. So it will not affect our comparison theorem
Now,
later on?
the sign of Lig does not
Yeah.
affect, doesn't, I mean, Ki. I mean, the sign of Lig affect y, y, yin. Why? Because basically we have this characterization of yin. Okay, as you can see here,
Yeah.
if the LIGs they are negative, this quantity will be positive and it could
Okay.
explode. Okay,
Yeah, I got you.
the end of the day, yin will converge to uh, to infinity. Okay, so in this
Ah,
case, I mean, in this case, the problem does not make sense. I mean, you don't have stochastic processes that are solution of the, yeah, it doesn't. I mean, the optimal payoff will be equal to in infinite, and then the problem is ill-posed. I mean, you don't have any
okay.
sphere.
Uh,
In the
yeah,
economic sphere, there is
I
no
got you.
unit which works in this framework in that way.
So, roughly speaking, it's actually like regret to switch. I mean, regret do not switch. Sorry, if you're not gonna. This is what's mechanical speaking. The K in this case. Could we say it like this or not? It's like, yeah, I mean, if you're gonna switch, you're gonna pay some cost. That's right. And if it is negative, in that case, it's like if you're gonna miss that opportunity, it's like you're gonna regret to do not switch in this mode.
Now you get to subsidy. If
Yeah, subsidy in that case.
Yeah, you get to
Okay,
subsidy because if I
okay,
don't you have some news from Europe or not, for example, because of the Hormuz Strait crisis in
yeah,
France. In France, the government pushes pushes car makers to skip from uh, uh, cars run with oil to cars which run with to electric cars. And I mean, when the government urges firms to do so, usually the government pays something. The government helps those companies to switch from one mode to
I
another one.
got you.
And in this case, actually, you decide to switch, but it's not a cost, but you get subsidy. So
Okay, I got you.
in which way you are going to behave or to manage optimally? I mean, if, for example, you are a car maker like Stellantis, like General Motors, like Toyota, and so on.
Yeah, I got you. So, just please one more questions about the Markovian case. I'm sorry for
Yeah,
a
sorry.
lot of questions about.
Yeah,
So it's very interesting to me.
thank you very
So
much.
for the Markovian case, I think slide number 30, yeah, you said that it's very difficult to consider the L with the diffusion process.
Yeah,
I mean, yeah, that's actually what I as I remember.
yes.
So could we say like I mean it's gonna be monotonic in T and with the fixed X? Could we extend it like this? Because some of the works, as I remember before, they consider actually the T and the X. I mean with the diffusion process here.
Now you know it's rather difficult to give. It's difficult to give deterministic function Lig
Okay. Yeah.
uh, of S, and when you which depends which depends on X, you will have Lig
Yeah.
of say T and X, and when you replace small x by the diffusion process, you have a monotonic stochastic process. Yeah, it's not. I mean, it's not natural. It's not normal assumption. This is why
Okay.
we have said that the now if I don't know, I should say that I don't know which kind of yeah. For example, you take Lig. If you take Lig C12, you use Ito formula, and then Lig, you will cancel the, you will, what are you going to cancel? Yeah, you will cancel the the stochastic integral part, and then you the other part, the finite variation part, will be inside, will be increasing or decreasing. Yeah, it's not something is
I got you. Yeah. Okay.
quite natural. This is what we have supposed that Lig does not depend on X in order to avoid, I mean, inequalities which do not provide more comprehension for the subject.
Okay. Thank you so much, Professor Saïd.
Yeah, thank you very much.
Thank you.
Thank you.
I'm very happy that you are happy. Where are you now?
I'm in Qatar, actually.
Okay,
I'm in
very
Doha.
nice.
Yeah. Okay. Yeah.
Have a nice time.
Okay. Thank you so much. Thank you.
Thank you, Professor
Nice to
Saïd,
see you.
for this nice talk. Thank you for the public. And see you maybe after 2 weeks. Eid Mabruk in advance. And thank you very much.